Okay, so we'll continue with another set of atomic structure practice questions. Okay, so the first one is, what is a wave? What is a wave? And then we need to explain the terms associated with the wave. That includes wavelength, frequency, amplitude. I can add on as well period, for example. It's also another term that you need to know. Okay, so what is a wave? So a wave is a periodic disturbance that moves in space. Okay, now for the sake of chemistry, we'll try to use a more formal definition. So a physical phenomenon described by these properties. Okay, so a physical phenomenon described by, so what are the things associated with a wave? So a wave should have the wavelength, frequency, amplitude, and a period. So any physical phenomenon described by its wavelength, frequency, and amplitude, or include period as well. Okay, so but we know that it's a periodic disturbance, of course. So to help you understand better, we can actually come up with a diagram that will help us even explain these terms that we're supposed to handle. Okay, so I'll give an example of the transverse waves. Let me even do something like this. Okay, so this is an example of a wave. One thing that you're able to see is that it's periodic. Periodic means it's repeating. Okay, so that is what a wave is. So this is an example of a wave. Now we can look at the properties. So if you are to measure the distance from the equilibrium position to the highest point, this is what we are calling the amplitude. Okay, so maximum displacement from the equilibrium position vertically is called the amplitude. Now, what is the wavelength? So the wavelength would be measuring from this point. We can either measure from this point to that point, or we can measure from this point, the crescent, to another crescent. Okay, that is called the wavelength. Or we can measure from a trough to another trough. Again, that is still the wavelength. Okay, so wavelength is referring to the distance between two crescents, between two troughs, consecutive crescents. Okay, meaning next to the other. Okay, so in other terms, wavelength is like the distance within which a wave or a cycle is complete. Okay, that is also another way we can approach the wavelength. And then the frequency. Frequency comes from the word frequent. How frequent is a wave? So how can we define the frequency? So the number of completed oscillations or cycles within a second. So measured in hertz, that is what we call the frequency. And then what about the period? So the period is basically the time it takes to complete a single oscillation or a cycle. Okay, so these are basically the things that you need to know about the waves. The formulas come in the other questions we're going to handle. Now question 2 is asking to list. So we've got part A and part B. Part A says list the types of electromagnetic radiation in descending order with respect to energy and frequency. List the types of electromagnetic radiation in descending order with respect to energy and frequency. So I need to mention to say the formula that is going to be very useful under the study of atomic structure. One of them is this one, which is of course Planck's. Okay, and then the other thing that you should know by now is that the V that is in this formula is representing frequency, and then frequency is inversely proportional to the wavelength, which means that if the frequency is higher, it means the wavelength is lower. Okay, so this very formula can be combined using a constant of speed of light So if we're to substitute in the Planck's formula, we're going to have, where there's a frequency, we can also put speed of light over wavelength. So this is another form of equation that you can use. Okay. So when they say list the types of electromagnetic radiation in descending order with respect to energy and frequency. So we're focusing on the ones with high frequency. Okay, and then we descend. We arrange them in descending order from the highest to the lowest. Okay, so in other terms, that means the wavelength is going to be in ascending order. Okay, so we're trying to arrange them in descending order in respect to energy, and then you've seen that from our formula, energy is directly proportional to the frequency, right? So this is the frequency, and then on the other end, we've seen that energy is inversely proportional to the wavelength. Okay, so therefore the highest in terms of frequency and energy that you need to know is, we've got the gamma, sometimes called the Y rays, and then we've got the X rays, we've got the UV, that's ultraviolet, and then we have visible light, and then we have infrared, and then we have the microwaves, and then finally the radio waves. Of course, under the radio waves, that's where you have the short, the medium, and the long waves. Okay, so now some of you are wondering, how can I easily remember this? So you can actually, one way you can easily remember, let me write for you something that can help you. So gamma rays has got the highest frequency, okay, and then radio waves has got the lowest frequency. Okay, so great X anchor usually visits, okay, so already we have the G, we have the X, we have the U, we have the V, and then usually visits in, and then we're remaining with just 2. So for the M, we can use March and then until retirement. Okay, so great X anchor usually visits in March, until retirement. Okay, so until is just helping us come up with a complete sentence. So if you can remember this, you're good. So great X anchor usually visits in March until retirement. Okay, if you can remember this, you'll be able to remember the order from the highest frequency. You know G is for gamma, X for X-rays. Okay, or I can remove usually, so that we can just say great X anchor visits in March until retirement. So the U for the anchor can represent UV, and then V for visible light, and then infrared there, and then we've got M for micro, and then R for radio waves. Okay, so that's it for question A. Okay, so we are now on B. So we are given representative wavelengths in the infrared, ultraviolet, and X-ray regions of the electromagnetic spectrum. And then what are we asked now? So we are taught to determine the energy of a photon of each radiation. Okay, so which has the greatest amount of energy per photon? and which one has the least. So what do we do? So one thing that we know is we already know that in comparison, from what we know, great ex uncle visits in March until retirement. So from there we know that obviously the one that is expected to have higher energy is the X-ray, and then the least should be infrared in this order. Okay, now we've been given the wavelength, so the formula that we're going to be using is this formula. So since we've been given the wavelength, we know that the formula is going to change to C over the wavelength. Since we know the energy and the wavelength are inversely proportional, and then we use a constant speed of light. The other formula that is useful that you can remember is frequency is speed of light over wavelength. These are inversely proportional. So the formula we have is C, that is, let me start with Planck's constant, hc over the wavelength. Okay, so we'll be substituting. So our Planck's constant is 6.626 times 10 to the power negative 84. The units are joule second. You know the units of frequency, we're going to be second negative, that's a Hertz. Okay, so multiply by the speed of light, which is approximately 3.0 times 10 to the power 8, and then of course divided by the wavelength. So to save on space, what I'll be doing is, we know that formula already, so we have infrared there, we'll write the answer there, and then we have the UV, and then we'll have the X-ray. So we'll just be plugging in the value of the wavelength. So beginning with the very first one, 1.0 times 10 to the power negative 6, that is for infrared. So grab your calculator. So 6.626 times 10 to the power negative 84, and then multiply by, so we'll multiply by 3 times 10 to the power 8. Okay, and then after that we multiply that, or we divide that now by 1 times 10 to the power negative 6. So 3 times 10 to the power 8, and then divided by 1 times 10 to the power negative 6. Okay, so the value I'm getting is 1.9878 times 10 to the power negative 31 joules. So we can now plug in the power negative 8. So 6.626 times 10 to the power negative 84, multiply by 3 times 10 to the power 8, divided by 1 times 10 to the power negative 8. So 1.9878 times 10 to the power negative 17. Okay, assuming I've done all my calculations okay there. And then finally 6.626 times 10 to the power negative 34, multiply by 3 times 10 to the power 8, and then divided by 1 times 10 to the power negative. So that would be to be power negative 10. Okay. So that is 1.9878 times 10 to the power negative 15. So for the very first one, it was an issue for calculations. Okay. So if you check, there's a difference of between 7 and 5. That's a difference of 2. So obviously we expect this to have a different power there, which should be also the difference of 2, which should be negative 19. So let me just redo that. 6.626 times 10 to the power negative 34, multiply by 3 times 10 to the power 8, divided by 1 times 10 to the power negative 6. Yes, So that is the order. So of course all these should have units, joules, because we are calculating the energy. So which one has got the greatest energy here? So just like we predicted, so X has got the highest, and then of course, so one thing that we are seeing is the one that had the greater, a longer wavelength has got lower energy, the lowest actually. So the one which has got the least is infrared in this case. Okay. So question 3, what is the wavelength in nanometers of a blue light having a frequency of 8.6 times 10 to the power 13 Hz? So we've been given the frequency to be 8.6 times 10 to the power 13 Hz. We need to determine the wavelength. So the formula we're using, energy is equal to hv, where v is our frequency. Now we know this formula can also be energy is equal to hc over wavelength if we're dealing with wavelength. Now this time around we want to find the wavelength. We've been given the frequency. So if you had to equate these two formulas and relate the frequency and the wavelength, you see that this is hc, this is hv. So since these are equal, right, we can equate what is on the right. So the formula is going to be hv is equal to hc over the wavelength. So that's common. So therefore frequency is equal to speed of light over wavelength. I already showed you this equation. This is the equation that relates the frequency and the wavelength. So for the very first one, first to determine the wavelength, we can just make the wavelength the subject. So it's going to be c over the frequency. So speed of light 3 times 10 to the power 8, and then over frequency 8.6 times 10 to the power 13. Okay, so whatever we're doing, we're using the standard units in. So we'll give us meters because the speed of light is in meters per second. So 3 times 10 to the power 8 divided by 8.6 times 10 to the power 13. Okay, my answer in scientific notation is a 3.4. So I'll take it to 2 decimal places. Looking at what we have there, I'll just set 1 decimal place. So 3.5 times 10 to the power negative 6. Negative 6 what? So the units are meters. So we want the answer in nanometers. So you know what? In nanometers, you can just basically multiply by 10 to the power 9. So if you multiply by 10 to the power 9, so we'll have 3.5 times 10 to the power 3 nanometers. Okay. So if we are to have it in a normal form, actually, it's going to be 3,500, but we can leave it there. So 3.5 times 10 to the power 3 nanometers. Okay. And then for the other part, they want us to find the frequency. So frequency, speed of light over the wavelength. So we need to take the wavelength in meters. So we'll have to multiply by 10 to the power negative 9. This is the difference when you're moving from a bigger unit, which is a meter, to a smaller one, nanometers. You need to multiply the meters by 10 to the power 9. When you're getting back to meters, which is bigger, you have to divide 10 to the power 9, which is as good as multiplying by a negative power. So 3 times 10 to the power 8 divided by 566 multiplied by 10 to the power negative 9. So the answer I'm getting for our frequency, 5.3 times 10 to the power. So this one is actually to 3 significant figures. So we can have 5.30 times 10 to the power 14. So frequency, that's in Hz. So this is how you handle this question. Simple and straightforward. Question 4. So part A says a photon has a wavelength of 624 nanometers. We need to determine the energy of the photon in electron volts. Okay, so whenever you're given the wavelength of the frequency, the formula that needs to come to mind is formula, Planck's formula. Okay, so in terms of wavelength, this is the way it comes out. In terms of frequency, we have a product of Planck's constant and the frequency. Okay, so let's plug in the values. Planck's constant is 6.626 by 10 to the power negative 34. The c, which is the speed of light, is 3 times 10 to the power 8 divided by the wavelength 624. Now nano means times 10 to the power negative 9. In other terms, we are dividing by that. Okay, so we can now determine the energy. So I'll start with the top, 6.626 by 10 to the power negative 34 multiplied by 3 times 10 to the power 8 and then divided by 624 times 10 to the power negative 9. 10 to the power negative 9. So the answer I'm getting for the energy there is 3.18 times 10 to the power negative 19. So that is in joules as our energy. Okay, and then we can now move to B, but before that we have to convert this to electron volts. So the conversion factor, 1 electron volt is equal to 1.602 times 10 to the power negative 19 joules. So you can put x here to represent the volts. So we're just going to divide by that value. Okay, so divide by 1.602 times 10 to the power negative 19. Okay, so that's giving me a value of 1.99 okay, electron volts. Okay, so that's how you deal with this conversions. And then if you look at B is asking us to calculate the wavelength, okay, where we're given a transition, okay, in the hydrogen atom. So, and then we're asked to determine also what the type of electromagnetic radiation is emitted, given n is equal to 3 and n phi is equal to 2. So calculate the wavelength of light emitted when each of the following transitions occur in the hydrogen atom. So in this case, it's a two-way thing. Since the question is so general, we have the transitions, and then we've not specified which one is the final and which one is the initial. Okay, so I'll consider one case where we are saying we have a transition from the second to the third, right? Okay, so where we have an electron moving from the second energy level to the third energy level as our final. So the first part is to determine the wavelength. So whenever you are determining the wavelength from transitions, the formula that can help you very fast is we call it the Rydberg equation, which is 1 over the wavelength, and then the Rydberg constant in meters is 1.097 times 10 to the power 7 meters negative, and then in the brackets you have a transition, so 1 over the initial squared minus 1 over final squared. So you just plug in. So 1 over the wavelength is equal to 1.097 times 10 to the power 7 meters negative, and then the initial we are taking to be 2, and then the final we're taking it to be 3, right? Okay, so for this transition, what do we expect? So 2 squared is 4, 3 squared is 9, so we can simplify that. 1 over 4 minus 1 over 9, 5 over 56 multiplied by 1.097 times 10 to the power 7. Okay, so we have 1 over our wavelength being equal to 1523611.1 meters negative. So we can make wavelength the subject. So our wavelength, since it's in terms of reciprocal, we can just divide 1 by whatever we have. Okay, so after dividing, the answer I'm getting, is, in terms of scientific notation, is 6.563 times 10 to the power negative 7 meters, because we used our constant in meters, so the wavelength is also in meters. Okay, now we've just calculated the wavelength. The other part of the question is asking us to, so by the way, you can also try the reverse. Since this is the transition we've assumed from 2 to 3, you can also try 3 to 2, you see what you're going to get. So I think the difference in terms of energy would be more on the sign, but you can try that as well and see the wavelength you're going to get. Expect the same answer. Okay, so we've determined the wavelength. Now, what type of electromagnetic radiation is emitted? What type of electromagnetic radiation? So usually we deal with the 3: infrared, and then visible light, of course, and UV. So you have to choose which one it is. So to help us to make this easy, the visible light is categorized between 400 and 700 nanometers. Okay, and then you know that UV has got a half frequency compared to the infrared. So this side, from the left to the right, there is an increase in frequency. So it's supposed to be the opposite for the wavelength. So UV has got a shortest wavelength if you compare the 3. So EA meaning that it's supposed to be less than 400 nanometers, and then the infrared is supposed to be greater than 700. So we're dealing with nanometers here, so it's better we convert the answer we have to nanometers. How do we do that? Since it's meters, we can just multiply by 10 to the power 9, right? So if I multiply by 10 to the power 9, the answer I'm getting is 6.56 times 10 to the power 2 nanometers. So assuming our calculations are okay, and looking at the value we have, if we can have it in normal, we can have a value of about 656.3 nanometers. So looking at this value is between 400 and 700, so we would conclude this in visible light. Okay, that's what we would say. If it was going to be greater than 700, we would say it's infrared, and then if it was going to be less than 400, we would say UV. Okay. Question 5. The first line of a Balmer series occurs at the wavelength of 656.3 nanometers. What is the energy difference between the two energy levels involved in the emission that results in the spectral line? So we're given the wavelength. So there are two ways of answering this question since we're trying to determine the energy. One way would be using this formula. Okay, since we've got the wavelength, this formula is going to work. Just convert the wavelength to meters, but I want to introduce you to a new formula. So the formula is negative 2 point, or let me just work with it in the positive form, 2.18 times 10 to the power negative 18, and then 1 over the initial squared minus 1 over the final squared. So why am I saying this? So Balmer series involves the movement of electrons to the second energy level, because the first one is called the Lyman series. Now the first, for the Balmer, it's the second energy level. So the first transition to the Balmer comes from the third energy level to the second. Okay, that's the first transition. So therefore the initial for the first to the Balmer series is 1 over 3, from 1 over 3 to 1 over 2 itself, which is involves Balmer series. So surprisingly, it's so interesting that if we try to calculate here, we're going to have in the brackets 1 over 9 minus 1 over 4 and then multiply by the 2.18 times 10 to the power negative 18. So the answer is negative 3.02, let me just say 3 times 10 to the power negative 19 joules. So why is it negative? So by now you should know that whenever you're having a movement of an electron from a higher energy level to a lower one, energy is lost. That's why it's a negative. Now what about if you try the other formula? Remember, in this calculation we've not even used the wavelength we are given. What if we use the wavelength? Are we going to get the same answer, or it's going to be different? So we can try it. So our energy is going to be hc over that. So 6.626 the Planck's constant, the power negative 84, multiplied by 3 times 10 to the power 8. This is over the wavelength, which is 656.3 times 10 to the power negative 9, because we are converting that to meters right away. So 6.626 times 10 to the power negative 84 multiplied by 3 times 10 to the power 8. So if we get to divide, we're going to get, so 656.3 times 10 to the power negative 9. So the value I'm getting there is 3.03 times 10 to the power negative 19 as well in joules. So you just remember that this was from the outer to the inner part, so it's a negative as well. So it doesn't matter actually. So any formula can work for this question. Question 6. Calculate the wavelength in nanometers of a photon emitted by a hydrogen atom when its electron drops from the 6th energy level to 4. Okay, so whenever I want to determine the wavelength in regards to transition, just use Liebeck formula. It's easy and faster. So the Liebeck's constant, and then 1 over the initial squared minus 1 over the final energy level squared as well. So the constant in meters, so 1 over wavelength is equal to, the constant in meters is 1.097 times 10 to the power 7 meters negative, and then the initial in this case was 6. We're going to a final one, which is like 4. So 1 over wavelength, so grab your calculator, 1 over 36 minus 1 over 16, 1 over 36 minus 1 over 16 multiplied by 1.097 times 10 to the power 7. So that's negative 380,902.7. So you can divide both sides, multiply both sides by the wavelength. So it's going to disappear on the left hand side, and then divide that value into a 1. So our wavelength value becomes, so by the way, the reason why this is giving us a negative, because the idea is when you're dealing with the energy, when an electron is falling from 6 to 4, it's supposed to be a negative, but for the wavelength, since this is a distance, we have to just take the moduli of a value so that we deal with a positive. So scientific notation, the value is positive 2.6 times 10 to the power negative 6. This is in meters. So if we are to find the answer in nanometers, as the question is requiring us to, we have to multiply by 10 to the power 9. Okay, and then have it in the normal form, so that we just approximate the value to be 2625. This is nanometers. That is the wavelength in that transition. Alright, so we'll look at question 7. So explain the statement matter and radiation have a dual nature. So earlier on we talked about the wave particle duality. That's the same thing we're talking about here. So the argument of the importance of this, or what it means when you say dual nature, it focuses on the idea that particles like photons and electrons that we study under atomic structure tend to exhibit both the properties of a wave and a particle. Okay, so for example, as a wave, you see that photons or electrons tend to exhibit interference. Okay, this is one of the properties that waves have. So we find that electrons may also be affected. Okay, and then you can look at other things that identify particles. Okay, so under a detector, for example, you can see that they do behave as discrete particles. So this shows that photons and electrons exhibit both a wave and particle nature in them. So it's dual, meaning that there are two different things found in one. Okay. B says, what is the de Broglie wavelength in nanometers associated with a 2.5 grams ping pong ball traveling at 55 meters per second? So we already talked about de Broglie wavelength, which comes from the wave particle duality. We said wave is equal to Planck's constant over mv. Okay, this is of course product of mass and velocity, which is equal to momentum. So this came from E is equal to mc, and then this is in terms of a particle, and then in terms of a wave, we know it came from a relationship that we expect to exist. Okay, so E is equal to hv as well. So combining the two equations, this is what comes up. So we need to find the wavelength. Planck's constant 6.626 times 10 to the power negative 84, that is joule-second, and then divided by mass. So we need to have our mass in grams, in actually kilograms. 2.5 divided by 1000, 0.0025 kilograms, and then multiply by the velocity, 35 meters per second. Okay, so of course we are using the standard unit, so expect to have answers in meters. Okay, so 6.626 times 10 to the power negative 34 divided by 0.025 multiplied by 35. So I'm getting a value of 7.57 times 10 to the power negative 83. That is our wavelength in meters. Now we want to advance in nanometers, so we can multiply by 10 to the power 9. Okay, so we have a value of 7.57 times 10 to the power negative 24 nanometers. So we can round it off to two significant figures. We've got two significant figures in all the cases. So even 7.6 times 10 to the power negative 24 nanometers. Okay. Okay, so how is the concept of electron density used to describe the position of an electron in the quantum mechanical treatment of an atom? So unlike the other classic models that we've talked about previously, where we've made an argument to say electrons basically tend to move or are found in what we call shells, right? Shells. Okay. So unlike this argument, for the quantum mechanics, the argument is based on what we are calling now electron density. So here we are told electrons get to exist in what are known as orbitals. Okay, so this argument of saying electrons are found in the orbitals, for us to determine the actual position or predict the position, we use what we call electron density. So where we have a higher electron density, that is where there is a higher probability of you getting to find the electron. So I'll repeat that. Of course, we've seen that electron density represents the likelihood of you finding an electron at a specific location. So higher electron density indicates a higher probability of you finding an electron in that region of an orbital. Okay, so like I mentioned earlier, this is different from what we've studied previously when you look at the other models which depict electrons to be found in the orbiting around the nucleus in well-defined paths. But under quantum mechanics, there is an introduction of the concept of the orbitals. Okay, so we can now look at B. What are we taught? An electron in a certain atom is n is equal to 2 quantum level. List the possible values of L and ML that it can have. So in the first set of atom practice questions, I explained well on how to determine the value of L and ML. So first of all, I said n is called the principal quantum number, which tells us or gives us the energy and the size of the energy level. So this is the way energy levels are. Okay, so n is equal to 1 for the first one, n is equal to 2. And then I said the value of L is the angular momentum quantum number, which is dependent on n. So it's given as 0 all the way up to n minus 1. So in this case, it's going to be 0. And then n minus 1 is what? 2 minus 1, which is just going to be a 1. So if we add a 3, we're going to have 0, 1, 2, because n minus 1 would be a 2 in such a case. So in this case, what values of L can it have? Can only have 0 and 1. Now for ML, I said it's from the negative of L to its positive. So for a case where we have got 0, for L is equal to 0, from the negative of 0 to its positive, ML is just 0. And then for L is equal to 1, from its negative, ML is going to be negative 1, 0, and 1. And I did explain what this stands for. I said L, the angular momentum quantum number, represents the shape of a orbital. So for 0, it's a S. For L, it's the P. Obviously, for 1, it's P. And then for 2, it's the D. And then, of course, for 3, it's the F orbital. And then the ML, which we are seeing below, represents the number of orbitals you can have. So this is a single orbital over the 3 orbitals, and we know each orbital can have 2 electrons. So this means in the s orbital, represented by 0, we only have 2 electrons. In the p orbital, it has got 3 orbitals, which tells us 6 electrons in total. So we found the values of L and ML for n is equal to 2. We can now look at C. C says list all the possible subshells and orbitals associated with the quantum number n if n is equal to 6. So n is equal to 6. That's the principal quantum number. This is the number of the energy level. Now we can look at L. L, I said, it's from 0 to n minus 1. So it means in this case, we're going to have from 0 all the way up to 5. 0, 1, 2, 3, 4, 5. Because n minus 1 is 6 minus 1, which is 5. So these are the values of L in this case. Now, the question says list all the possible subshells and orbitals. Okay. So we've listed now the possible shapes of the orbitals. We can now go into determining the MLs, okay, which represent now the subshells. Is it the subshells? Yeah, subshells. So ML, I said, from the negative 1 all the way to its positive, right? So you can start. For L is equal to 0, it's going to be just ML being equal to 0. And then for L is equal to 1, it's going to be ML is from the negative to its positive, which would be negative 1, 0, and 1. And then for L is equal to 2, it's going to be from its negative as well. Negative 2, negative 1, 0, 1, and 2. So this applies to all the other L values you have. You continue indicating as such. Okay? So if, for example, from where L is equal to 5, it will be from negative 5, negative 4, all the way up to 5. Okay, so these are the possible orbitals you can have, and this tells us that we can have up to how many orbitals are these? These are like 11. 1, 2, 3, 4, 5. Should be 11. 11 tells us times 2, that is 22. Okay, so this is, well, usually focusing on the, this is the S, this is the P, this is the D, S, P, D, F. So we usually end on the F. Okay, so that's how you determine, of course, the possible subshells and orbitals associated with the principal quantum number. Okay. Now look at question 9, which says we have to explain the meaning of diamagnetic and paramagnetic. So I think this focuses on a concept of electrons being paired. Of course, Pauli exclusion principle tells us that no two electrons can have the same or set of 4 quantum numbers. Okay, so in a single orbital, we know an orbital can have 2 electrons only. One is supposed to face upwards, the other one downwards, indicating that the magnetic spin quantum number is different. The one facing up is positive half. So all the other 3 set of quantum numbers would be the same, but the 4th one would be different. Okay, so now the argument is, in a case where you have, let me give an example of 1s, 2s, and then let's talk about 2p. So in a case where you have electrons just being like that, where they are not paired, where there's only a single electron in a given orbital, that is said to be paramagnetic, meaning that electrons are not paired fully. And then the magnetic focuses on a case where they are paired. When electrons are fully paired, that is said to be diamagnetic. And of course, there's a bit of some attraction, weak attraction to paramagnetic, and then diamagnetic, there's no attraction, no weak attraction at all that can actually be observed. Okay, so I've said diamagnetic refers to unpaired electrons, okay, and are not attracted to any magnetic field. So all the electrons are paired. Then for paramagnetic refers to they have unpaired electrons. So diamagnetic does not have any unpaired electrons. Paramagnetic does have unpaired electrons, which are weakly attracted to a magnetic field. So examples would be, let me give simple examples. I think that would be helium for diamagnetic and then oxygen for paramagnetic. So of course we know oxygen, for example, has got that's 6, right? That's the atomic number of oxygen. Is it 6 or 8? It's 8 actually. So it's 8. And then if you try to substitute, we're going to have 1, 2, 3, 4. And then how many more do we need? So we have 4 already. So 5, 6. So we have 6, and then 7, and then 8. So see, there are 2 electrons that are unpaired there. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So there are 2 electrons that are unpaired there. So this makes this to be paramagnetic. Okay, there's a set of electrons that are unpaired. For diamagnetic, no electrons are unpaired. Of course, helium should be the second. Okay, so only 2 electrons which are paired. So this makes it to be diamagnetic. So it's not attracted to, there are no weak attractions to a magnetic field. Okay, so whenever you want to tell whether a specific atom, is like diamagnetic of any element, just try to, fill in the orbitals like I've did there. It will show. Okay. So the ground state electron configurations listed here are incorrect. We need to explain what mistakes were actually here. So I would advise you get your periodic table and then get the atomic number of these atoms and then try to write our own so that we can easily identify the mistakes. So starting with atomic number of aluminium. So atomic number of aluminium is 13, and then atomic number of that should be boron, right? It's boron 5. Then atomic number of fluorine, that should be 7. Fluorine. So atomic number of fluorine is 9. Okay, so if you've watched our video, that is the introduction to the study of the electron configurations. I already showed you on how you can come up with electron configuration. So 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So I said this is the way you move from 1s to 2s, 2p to 3s, 3p to 4s, 3d to 4p, like that. So we'll start. How many electrons do we have for aluminium? 13. So 1s2, 2s2, 2p, p gets 6. So how many do we have already? 2, 4, 6. Are we done? 6 plus 4, 10. We're remaining with 3. So now go to 3s and then 2. Are we done? So 2, 4, 10, 12. And then you can go to 3p1. Okay, so that already tells you what is paramagnetic, right? Boron, 1s2, 2s2, that's 4. 2p1, that gives us 5. Fluorine, 1s2, 2s2, 2p6, that's 10. That's already more, so we need to reduce to 5. 5 plus 4, 9, right? So that's how you come up with electron configuration. So you can see where the errors were, right? Can move on to the other question.